In engineering, from a mathematical standpoint, one of the most important things to understand, in which a lot of engineering analysis is based on, is the concept of a vector. So this lesson is going to get us used to using vectors and defining what a vector actually is. So what we want to do to start off with is we want to compare what a vector is to what we're normally used to working with, and that is a scalar. So a scalar is nothing more than a quantity expressed by a single value. Typically, that value is what we call a magnitude. Some examples of scalars that you've worked with are time. How much time does it take to accomplish a task? That would be a magnitude of time. Temperature. What is the temperature outside? Again, that's just a single magnitude that tells us how hot or cold it is. Another one might be speed. How fast are you traveling? Are you traveling slow? Are you traveling fast? Are you traveling somewhere in between? There are lots of different values that are represented by scalars, simply quantities that only have a magnitude. Now, what is a vector in comparison to that? A vector doesn't just possess magnitude, it possesses both magnitude and direction. Magnitude and direction. An example of something that possesses both magnitude and direction might be velocity. Now, velocity is sort of related to speed, except velocity, when we use in the sciences the term velocity, we're implying not only how fast something is going, but in what direction. So the velocity, saying 10 miles per hour, is only half of what we need. We would say maybe something as 10 miles per hour due north. Now I have both the speed and the direction, both the magnitude of my velocity and the direction of my velocity. It would be similar to saying to somebody that's never been to Oregon, something to the effect of, well, you're in Salem and Portland is only 55 miles away. Well, the question would be 55 miles in what direction? Well, you'd have to say north. So again, implying both magnitude and direction. Another idea that has the concept of a vector is force. And we are going to use vectors to represent force a lot in this course. Now, force, maybe you could imply that there's 30 pounds of force, but that 30 pounds does a number of different things depending on what direction it's going. So maybe 30 pounds of force to the right. And depending on your scenario, that 30 pounds of force to the right could do something completely different than 30 pounds of force to the left. And especially when we're looking at multiple forces together, we need to know the direction that they're acting so that we can determine what the forces are doing when we combine them all together. So a vector is something that possesses both magnitude and direction. Okay, so that's the important piece to remember about vectors. So how do we represent a vector? Depending on what textbook you look in, vectors are represented in many different ways. One of the most common ways that a textbook represents a vector is with a capital letter typically, and then they write the capital letter in bold. So maybe we say vector U. The hard part is when we're just drawing on paper, it's hard and tedious to continually represent something as bold or not bold, because the same letter unbolded means something different. So here's how we're going to do it. To represent a vector, we are simply going to put a half arrow above it. So this right here would be the vector of u, the vector u. Now, vectors are represented by arrows. So maybe vector u is an arrow that looks like this. Now you'll notice that this arrow has a specific length. That length is representative of the magnitude. It's also pointing in a specific direction. Okay, so this arrow possesses both magnitude and direction. In contrast, maybe I have another vector, let's say vector A over here, so A with an arrow above it. Maybe vector A doesn't have quite as much magnitude, so we draw it shorter relative to vector u to show that it has less magnitude, and maybe it's acting in a different direction, so the arrow is pointing in the different direction. Now, the starting point of a vector we call the initial point of the vector. Where the arrow ends, we call the terminal side. So we have the initial and terminal side of a vector. That's going to become important as we take a look at how we add, subtract, and multiply vectors. Now, if we want to only express magnitude of a vector, what we simply do is put the vector letter in between two lines. So for instance, the magnitude of vector A, we would simply write it as vector A in between two bars. That right there is the magnitude of vector A. If we wanted the magnitude of vector u, we'd represent it as the u vector in between two bars. So if we draw two bars, one on each side of a vector, what that is implying is that we only care about the magnitude. We're going to set direction aside, and we're only looking at magnitude. Okay, so vectors are represented by arrows. We label them with capital letters, and we put half arrows above them for us to represent, to make sure that we understand that they are vectors. And then to represent simply the magnitude of the vector without worrying about the direction, you put a bar on each side. Now sometimes a vector is represented again by an initial and terminal point. Let me draw another vector here. Sometimes the initial point is represented by a letter and the final point is represented by a letter. So in this case, we would represent this vector as AB with the arrow above. AB with the arrow above. So, vector representation, again, is done by graphically by arrows, and then we use capital letters to represent them, sometimes two letters describing the initial and the final point are what we use to describe the vector. So what we want to do now is we want to look at a visual representation of vector addition, subtraction, and what's called scalar multiplication. So to do this, I'm going to start with two vectors. I'll start with vector here. I'm going to call this vector A. And then I'll draw another vector over here in a slightly different direction and a different magnitude. It's a little bit shorter. And we will call this vector B. Okay. Now the initial and terminal sides are important because what we can do from a graphical standpoint to add two vectors together, we simply take the initial side of one and put it in the same location as the terminal side of the other. So for instance, if I wanted to figure out what A plus B was, I would simply take my A vector Make it a little bit longer so that it matches both the magnitude and direction. And then I would take my b vector, and the tail of my b vector I would put at the initial side of my b vector, I would take and I would put at the terminal side of my a vector. So it would be something like that. So now the addition of those two vectors would actually be the vector that starts at the initial point of A and ends at the terminal side of B. So it would start here and end there. So that green vector is A plus B. That green vector is A plus B. So there's a visual representation of what the addition of two vectors would look like. Well, what about subtraction? What about subtraction? Well, with subtraction, what if we wanted to do A minus B? A minus B, what would that look like? Well, we're starting with A. So I'm going to draw my A vector again. And I'm actually going to move it just a little bit down. So here's my A vector. Now instead of drawing my B vector the way it is, I'm actually subtracting the B vector. So what I'm going to do is, when you are subtracting, you're essentially making that vector B negative. By making it negative, it does not adjust the magnitude. It only adjusts the direction. So by making a vector negative, you swap the direction in which it's traveling. So the B, which would normally be like this, I'm actually going to draw in the exact opposite direction, that way. So that would be the negative B. So we have our A vector, and then this essentially is our negative B vector. So A minus B would end up being the vector that starts at the initial of A and ends up at the terminal of the negative B vector, because we are subtracting. So there's a vector addition and vector subtraction from a visual standpoint. Lastly, we want to talk about what's called scalar multiplication. You can take any vector. We'll take vector A as our example, and I want to do 3 times vector A. Well, when you multiply a vector by a scalar, notice I say scalar because 3 is just a quantity that has a magnitude but no direction. I'm just multiplying by a scalar. So what I could do is I could take my A vector and I simply take and stack 3 of them together in the same direction. So literally multiplying by 3. So my 3A vector would actually be the vector starting at the initial of the first and at the terminal of the last of the 3 vectors. So there would be my 3A vector. So these are the visual representations of what it looks like to do addition of vectors, subtraction of vectors, and then a scalar multiplication of vectors. Now, in and of themselves, it's not too incredibly awe-inspiring. We're just playing around with arrows, manipulating. Where this becomes significant is when we start applying it to physical scenarios. So to end this, we're going to take a look at our very first physical scenario of forces. Okay? And it's going to require us to add vectors together. And we're going to walk through the process of how do we use this visual representation to help us. So it says this, in figure 2.11 is an initial design sketch of part of the roof of a sports stadium that is to be supported by cables AB. Looks like cable AB is right here. And then cable AC. So we got 2 cables holding up the side of a structure that's holding up a roof. The forces the cables exert on the pylon to which they are attached are represented by the vectors FAB. So over here, they've drawn that. Here's FAB and also FAC. Now the magnitudes of the forces, FAB is 100 kilonewtons and FAC is 60 kilonewtons. It says this: determine the magnitude and direction of the, here it is, the sum of the forces exerted on the pylon by the cables, graphically and by using trigonometry. So we've got two forces. One of them, the 60 kilonewton force, is acting completely horizontally, so you know magnitude and direction. The other force, FAB, has a magnitude of 100 kilonewtons, but it's acting 30 degrees, we say, above the horizontal. So a horizontal line, they are 30 degrees above that horizontal line, and that's the direction that FAB is acting. So here's what we're going to do. We want to find both the magnitude and the direction of these two forces added together. So to do that, what we're going to do is we're first going to start by drawing a picture. What we're going to do is we're going to take those two forces. Here we've got our FAC, and here we have FAB. And we know that the angle measure between them is 30 degrees and that the FAC is horizontal. What I'm going to do is I'm going to move FAB into a position where it graphically shows these two vectors added together. Well, we saw that up there in that we could take the initial side of one and put it at the terminal side of the other. So to do that, what I'm going to do is I'm going to copy the FAC again right here, but then the FAB, I'm going to start at the terminal side of FAC. And then I know, I'm going to use a dashed line to represent the horizontal, that this angle here is 30 degrees. So what I've done is I've taken FAC and FAB, which are vectors, so I better put the arrows above them, and I've arranged them graphically in a way that shows that I'm adding them together. And from what we saw above, we know that the sum of those forces is represented by the vector that starts at the initial of one and ends at the terminal of the other. So that dotted line right there is the vector that we're interested in. That is the vector FAC plus FAB. Okay. So that's what we're supposed to find. Now, what we're going to find out is that in order to solve addition, subtraction of vectors, one of the skills that we're going to have to remember from previous math classes that we've taken is trigonometry. We are going to be using trigonometry a lot in this course in relation to our manipulation of vectors. So here's how we're going to approach this. What I'm going to do is I'm going to draw this again as a triangle. And I'm going to, on this triangle, put down the information I know. I know that FAC, the magnitude of it is 60. I know that FAB is 100. And I know that this angle right here is 30 degrees. Now, if that angle there is 30 degrees by supplementary angles, I know that this angle in here is 150 degrees. Okay, so I now know three pieces of information, two sides and an angle of my triangle. Now, there's two different laws that we're going to have to remember in order to find the information we want. What we're after is, number one, the magnitude of the sum. So I want to know the length of this side of the triangle. The other piece that we're after is the direction it's acting. I want to know this angle measure so I know how much above the positive horizontal I'm acting when I add these two forces together. So the first law I'm going to use is the law of cosines. Now I'm going to label this as A, B, and C. We remember from the law of cosines that C squared equals A squared plus B squared minus 2AB times the cosine of angle C. Well, angle C is the angle opposite of side length C. So what we have here is C squared is equal to, well, we already know the magnitude of A, that's 60, so 60 squared, plus, we already know the magnitude of B, that's 100 squared, minus 2 times A, which is 60, times B, which is 100, times the cosine of angle C from supplementary angles we found was 150 degrees. So if I solve this now for C, I end up getting, and do this on your own to verify, that C is 155. Now 155 what? If we go back up here, we notice that the units of the force that we're operating in is kilonewtons. So we know that the sum of these forces together is 155 kilonewtons. Great, so we now know the magnitude of the two vectors added together, but I also want to know direction. For direction, we're going to need another law, the law of sines. We remember from the law of sines that we can pair up in a ratio a side length and its opposite angle. So for instance, what I'm going to do to figure out this angle right in here, I'm going to label this angle as alpha, the Greek letter alpha. That's the angle I want to find. So what I'm going to do is, I know the combination of side length C now that I solved for it and angle C. So I'm going to go 155 divided by the sine of the angle opposite of that is 150 is equal to, well, what's the side length opposite the angle measure I want to know? Well, that's 100 divided by the sine of its opposite angle, which is alpha, the angle that I'm looking for. So we've set it up, and we can now solve for alpha. So to solve for alpha, we could work through, simplify, but as we do this, you do it on your own, check the work. I'm getting an alpha of 18.8 degrees. So when all this information is put together, when I add these two vectors together, what do I end up with? I end up with a vector that has a magnitude of 155 kilonewtons. So I'm going to say that our resultant force, so FAC plus FAB is equal to 155 kilonewtons, that's the magnitude, at 18.8 degrees. I want to indicate what direction, so I'm going to say counterclockwise. From the positive horizontal. Remember, clockwise, if you've got a clock here, clockwise follows the arms of a clock, and counterclockwise goes opposite the way the arms of a clock move. And then from the positive horizontal, we know that horizontally to the right is positive. And there we go, we've solved our first problem involving the addition of forces. So again, the concept is we can represent vector information using arrows and graphically represent that, and then utilize what we know about trigonometry in order to solve for what we are asked to solve for. and the end result gives us both still, because it's a vector, a magnitude and a direction.